Good morning to the students in mathematical thought and practice. We are coming to the end of the second unit of our course. And so right now, if you're my student this semester, what you're doing this week is you're working on our second exam. And so today's live stream is all about dedicated to doing some review for that exam and just doing sort of a flyover of the material that we've been talking about for the last couple of weeks with the goal of just kind of hitting the high points, making sure that you're taking away from this unit the most important bits of understanding. So here's the agenda for what I'd like to talk about. First of all, the biggest thing to know about this chapter, really, this whole unit, is how to tell the difference between a linear function or linear behavior versus exponential functions, exponential behavior. So that's the first thing that I want to really kind of dwell on. And when we talk about linear versus exponential, it's about understanding the difference between the types of arithmetic that are involved in constructing those two types of relationships. Linear functions are built completely on relationships between additions and subtractions, whereas exponential functions are built on relationships between addition and subtraction of one quantity and multiplication and division of the other. And so for that reason, linear functions are characterized by having a constant slope, a constant amount rate of increase or decrease, and exponential functions are defined by having a constant base, a constant percentage rate of increase or decrease. And so when we start talking about exponential functions, we're talking about percentage changes. And so I want to make sure that we also hit the high point of how do we understand how to measure and then how to apply percentage changes to quantities. And then probably the step of algebra that is the most confounding in this chapter, which is also probably puts it in the running for the most confounding thing in this entire course of mathematical thought and practice. And that is, how do we use logarithms to be able to solve exponential equations? How do we, in other words, use a logarithm to rescue a variable like x from out of the exponent in an exponential expression? We could dive down a pretty deep rabbit hole of logarithm stuff if we really wanted to, but I just want to make sure that we understand how to use logarithms as a tool to solve these equations without getting lost in all of the rich and interesting and for most people flash in the pan algebraic properties that logarithms have. So we just are mostly interested in them as a tool for helping us to solve certain types of equations. So that's the plan, that's the agenda for what I'm hoping to do with our time today. And it looks like I'm having a little bit of trouble with my feed, so just give me a second here to try and clean some stuff up. Don't know what's the issue here. Let's try this one more time. There we go. Sorry, let me just get this reconfigured. Looks like we're back, but my camera is a little bit out of adjustment. There we go. Okay, so let's get going with the question about how do we understand what is really the difference that matters between linear relationships and exponential relationships. So funny story, I actually did a quick Google search just before our live stream today. I went online and said, oh, what are some good data-driven resources that can help us to understand the difference between linear and exponential? And so I did a Google search for linear versus exponential data. Let me show you what actually turns up here. Linear versus exponential functions data. I do a Google search. There's a Quora article that's kind of talky about it. There's a Khan Academy video which does a pretty nice job of explaining it. I'd recommend you take a look at this video if you have a chance later. But the third link is actually a worksheet. It's like a project that's being used in a high school. And I click into the link and I find out that this is actually being used at the high school that I went to when I was in high school in North St. Paul, Minnesota, of all places. They managed to do really well on Google PageRank, and so it ends up being the third link on the list. So whoever's doing the search engine optimization for School District 622 in North St. Paul, Minnesota is doing a fantastic job. So here's the resource. It asks us to consider two different possible places to invest our money. One of them is at TCF Bank, which happens to be a local name for a bank in Minnesota. I used to have an account there before I moved away to college. And this particular account gives you $100 at the end of each year, and that's how you accrue interest on that account. Also, there's a choice of a Wells Fargo bank account that earns a 6% amount of annual interest. And so this project is all about figuring out which one of these two banking models is more beneficial. And what I like about that question, I really like a lot about that question, but it's a nuanced question because more beneficial, it can be understood in a lot of different ways. So what I want to do is help us just sort of unpack the information that we have here about these two accounts to highlight the difference between linear and exponential behavior, and then also to develop algebraic formula models for each of these accounts and use those models to answer some questions about how your balance of your money, your investment, is changing in this problem. And as much as I want to applaud my former school district for having this really nice resource that's here, it's available on the web for us to use, one thing I don't like about it is that the very first thing that this exercise asks you to do is to take the information that's given and immediately write an equation. And that is not my speed, especially in a course like ours, where I put a high priority on us being able to talk about these concepts, not just by diving directly into algebra, but by dwelling on the other ways of communicating mathematical thought first, by thinking about constructing a data table, and by thinking about constructing a graph. So I want to be able to do both of those things before we get to the equation question, because this is where we're really, I hope, going to understand best the difference between linear behavior and exponential behavior. So let's do the following. I'll get my browser window back up here, just sort of in a sidebar. So rather than have my first task be to discover an equation for these relationships, the first thing that I want to do is I want to construct a data table. In other words, I want to communicate numerically first, before we try to communicate algebraically. And this is a step I will always recommend to any student thinking about this, because it's a lot easier to think about numbers first and then think about variables and formulas and equations after, because the data should lead you toward the function and not really so much vice versa. So what I'm going to do is I'm going to just open up a Desmos window here. Again, this is a free online graphing calculator that I encourage everyone to use for purposes like this. I'm just going to open a data table over here on the side. I'm going to go back to the information that we're given here in the problem and figure out what information is important. First piece of information I see is that we're starting this initial savings, initial deposit, with $1,000. And when we say initial here, what we're going to use initial to mean is we're going to use this to mean time equals 0. So just whenever we start measuring time, I mean, time is one of these things with no beginning or no end as far as humans are concerned, right? And so we can set time equals 0 to be wherever we want it to be. So we'll just set it as whenever we open this particular savings account. We're going to call that time equal to 0. And so at a time of 0, this account has $1,000 in it. We're thinking of that as our initial deposit. So over here in my graphing calculator, I'm going to put in a 0 for my x variable, my independent variable, my time variable. And then for the corresponding value of y, I'm going to put in $1,000. And this would be a good time for me to change the scale on my graph so that I'll be able to see more of what I want to see. Maybe I'll set my x, my time range, so that I can look out, I don't know, 20 or so years into the future. So just make sure I have 0 through 20 on my x-axis. And this is going to be time since investment in years. So that's my x variable. And then value of investment in dollars. That'll be my y variable. And since I'm starting with $1,000, I need to make sure that I can see quite a bit of my axis here. So maybe I'll go from minus $500 on the one hand to $5,500 on the other hand, just so I've got enough room on my y-axis so that I can see quantities that are measured in thousands of dollars. Okay. So this initial deposit, this one observation here, gives me one data point on my graph. It gives me one ordered pair in my table of data. So let me put in a note here that what we're going to want to do is to find a model, an equation model, for both the TCF bank account, which earns exactly $100 at the end of each year, and for the Wells Fargo model, which earns 6% at the end of each year. Right? So the model that I just started graphing here, this green data point, is actually the initial data point for both of our models. And I think Desmos is nice enough that we can create a second y value in my data table here so that I can put my second data point. So in the green is going to be my TCF Bank model, and the Wells Fargo we'll put in purple. And so at 0 years at my initial investment, both of these points are at the same spot. Right? So now where do we go from here? How do I create more data points to fill out my data table? And as I create more data points, we'll be able to put more ordered pairs on the graph as well. So let's look at the model of change that's being proposed for each one of these accounts. The TCF Bank account is earning exactly $100. It's earning a fixed amount of money each year. So let me write that over here. So TCF Bank. What's happening in this bank account is it's increasing by $100. So I'm adding 100 every year to the value of that account. And the most important symbol that I just wrote down here in talking about this TCF account, for our purposes, the most important symbol to pay attention to is that addition sign right there. Whoops. What did I just do? Uh-oh. I seem to have just lost some bit of my annotation. Let me jump back into that real quick. Every once in a while, my iPad has a little hiccup. Oh boy. Okay. Let me just quickly write back down what it was that we had to work with. Oh boy, this thing is really giving me trouble all of a sudden. Let me real quickly go back and get a fresh... I've got to get myself a fresh screen here. So just give me a second. Here we go. All right, yeah, again, the perils of doing math live. This kind of thing doesn't happen on a whiteboard, but sometimes it happens when you're using technology. Okay, so again, what we're doing here is we're quantifying what happens with each one of these bank accounts. The TCF bank account adds $100 at the end of each year. And the most important piece of information right there is not the amount, not the number 100, but rather the fact that that $100 is being added to our account every single year. Because that is being contrasted with the Wells Fargo account in this project, which increases by 6% each year. And increasing a quantity by 6%, remember, when we talk about applying percentage changes, there are two ways to think about what increasing a quantity by 6% actually looks like from the standpoint of arithmetic. Because increasing a quantity by a percent requires us to do two types of arithmetic. It requires us to do a multiplication to figure out 6% of what. That 6% of what question is answered by multiplication of a quantity by 6%, or 0.06 as a decimal. So we have to do a multiplication, but then also we have to achieve this increase, which requires us to do an addition after the fact. So we have to do both a multiplication and an addition. And as I've been trying to suggest to you every time we talk about this topic, my preference is that we do the addition or subtraction first and the multiplication or division afterwards. So what I'll do is I'll take my 6% and I'll add it to 100%. Because to increase a quantity by 6% is to take the original amount of my quantity, my original 100, and then add onto it 6% of that same quantity. So in total, what I'm doing is I'm going to end up with 106% of my original quantity. But this of here, to take a percent of a quantity, means to multiply that quantity by the percentage that we have here. So 106% of a quantity can be found by multiplication of that quantity by 106%. And as a decimal, 106%, remember, is the same as 106 per 100. In other words, 106 divided by 100, which is another way to say 1.06. So as a decimal, 1.06 is what we end up multiplying my Wells Fargo balance by at the end of each year. And so the first thing to notice is the difference here between the types of arithmetic that are being used to change our quantities. Here, the fact that I am adding or subtracting means that the nature of the change here is an amount change. It's a dollar figure that's being added or subtracted each year, right? And this is going to be the kind of change that's going to correlate for us to a linear model. Meanwhile, for the Wells Fargo account, there is a constant percentage increase in the balance at the end of each year. And so what that indicates to me is that the arithmetic that's being used to change my quantity this time is not addition or subtraction, but it's multiplication or division. And multiplication or division, when it changes a quantity, is changing that quantity by a percent, not by an amount. And it's a constant percent change that characterizes exponential functions. So already I'm kind of giving away the game here, right? That when we model the TCF account and how its balance changes over time, we're going to expect to see a linear function. We're going to expect to see a straight line when we model that behavior. Meanwhile, if we were to model a Wells Fargo account, we would expect, because the percentage change is consistent year over year, we're going to expect that this graph is going to be the graph of an exponential function. So it's going to have a curve to it. And since it's an exponential increase, it's going to be a curve that curves upward as the graph goes from left to right. So with that as the backdrop of our expectations, let's go back to our data table and start trying to fill in some additional data points. So let's start with the Wells Fargo account. This is the one that's going to be shown in green. And let's think about how much money is going to be in that Wells Fargo account at the end of the first year. So this account, sorry, not Wells Fargo, TCF, the green account, right, which is changing by an addition of $100 every year. So we already know for the TCF account what the amount of the change is going to be year over year. Every year we're just going to add $100 to the balance. So if I'm starting my TCF account with $1,000 in it, then 1 year later, what I want to do is I want to add $100 to that account. And so I'll end up with 1,100, right? 1,000 plus 100, 1,100. And then if we can go forward one more year, let's just do it. At the end of year 2, we would be yet again adding another $100 to that value of that account. So every year that passes, the amount of additional money that we're getting in this account remains the same. It's a constant amount rate of change. $1,200 at the end of the second year. $1,300 at the end of the third year. Add another $100 the next year. Add another $100 the next year. And I'm going to keep going on this. 1,600. Let me skip ahead. I'm just going to use a little mental arithmetic here. Skip ahead to year 10. In year 10, we would be at $2,000. In year 20, we would be at $3,000. So here are some data points that show how this TCF account, the one that's changing by a constant amount rate of change of $100 at the end of every year, is changing over a 20-year period. And sure enough, when I plot this on a graph, I'm seeing the graph emerge as a straight line. And so because the arithmetic that we used here to analyze the changes, apply the changes for this Wells Fargo account, is only addition and subtraction, this tends to be most people's comfort zone. And linear thinking tends to be people's default position. When we think about rates of change, very often the first place that our minds go is to think about rates of change as being amount rates of change, and think about changes as happening via addition and via subtraction. So when we start to change the game and think about change phenomena that occur with a constant percentage rate, we're having to flex muscles that we don't have to flex very often, cognitively speaking, because we have to shift to thinking about change as something that happens by addition and subtraction, to thinking about change as something that can happen via multiplication and via division. But don't let that fool you too much. Just think instead about replacing what used to be addition of 100 as the way to communicate my change year over year with multiplication by 1.06, which, mind you, is a more challenging mental math problem to do. It's much harder to multiply a quantity by 1.06 than it is to just add 100 to a quantity, just because multiplication is a cognitively more challenging operation than addition or subtraction. But fortunately, we have technology, calculators and computers and things like that that can help us with the grunt work of actually filling out the rest of this data table for my Wells Fargo account, which every year I am multiplying its quantity by 1.06. So for my Wells Fargo account, in year 0, it has that same $1,000. But then 1 year later, how do I know how much is in this account? I have to multiply that number by 1.06. That is how we effect a 6% increase in a quantity. And so you pull out a calculator, you multiply 1,000 by 1.06, and you find out that at the end of that first year, this account has $1,060 in it. And so my first purple data point ends up right here. Then I want to multiply that quantity again by 1.06. So 1060 times 1.06 to figure out how much money I have the year after that. So pull out a calculator, or I'm using just my browser's search window to figure out the value of this. It's $1,123.6. $1,123.60 at the end of that second year. 1123.6. So there's my next of my purple data points. Then I'll multiply that again by 1.06 to find out where we're at the end of the third year. 1191.016. You might want to round that to 1191.02 because we're talking about dollars and cents here, and so fractions of a penny are things that we might carry with us in calculation, but we might not always communicate to somebody who's asking the question. But let's not let that stop us from just putting that number down. Don't worry about rounding it. I don't worry too much about that in our class. One more multiplication by 1.06 puts me at 477. I'm rounding just a little bit, but again, I don't really care. Multiply by 1.06 again, 1338.226. Multiply by 1.06 again for the end of year 6, 1418.52. Okay. So one of the things that you should be noticing here is that immediately we can answer one question about these two these two bank accounts and what's happening with our balance in both of these cases, right? Because if you look closely at the data, it looks like for the first 6 years of these particular accounts, at least, it looks like the TCF bank account is going to have a higher balance year over year than the Wells Fargo account. So for those first 6 years, it looks like it's better, it's more advantageous for an investor to be earning $100 every year than to be earning that 6% at the end of every year, right? Just based on the data that's in this data table alone. The green curve looks like it's above the purple curve. And so something interesting then happens if we try and extrapolate this out to the 20-year mark. So at the end of that 10th year, the TCF bank account, the green one, is actually still leading. At the end of that 10th year, we're at 1898.30. But at the 20-year time horizon, suddenly we have it the other way around. At the end of that 20th year, we're at 3399.56. Okay. So if you wanted to know where those numbers come from, just continue that same process of just multiplying by 1.06 over and over and over again. Right. Ultimately, we're going to make a formula that will do that work for us without all of that intermediate work. But for now, let's just imagine that that's what I did. I just multiplied by 1.06 enough times to get me from the 6th year to the 10th year, and then from the 10th year to the 20th year. So if the question is, which account is better? The answer is, it depends. right? It depends on how long you want to have that money in the account, right? At least until the 10-year mark, at least until year 10, the TCF account has a higher balance each year. But by the 20th year, the Wells Fargo account has a higher balance, right? So that is a classic example of the kinds of questions that I want us, you all, to be able to ask and answer about quantitative and mathematical information. Because these are the kinds of messy questions that you encounter in the real world outside of your math textbooks, right? Math textbooks, when they ask you a question, tend to ask you a very carefully constructed and curated question that gives you exactly as much information as you need to solve it, and it's in the same section of the textbook as exactly the technique that you need in order to solve it, and it's all this very carefully walled off and protected environment. And so you don't have to look very hard or reach very far to figure out how to address a question, and the question has a black and white yes or no answer. That's not reality. It's not reality when we talk about sort of critical thinking in general, and it's not reality when we think about quantitative reasoning and literacy specifically. The kinds of questions like the one I highlighted here, which account is better, those are the questions I love, because the best questions that I want students to think about in college are the questions whose answer is, it depends. And the process of thinking critically about quantitative information is the process of digging in and figuring out it depends on what, and why does it depend on that thing, and how does it depend on that thing. So already, this particular question, which account is better, we can say it depends on how long the money is going to stay in that account. If it's going to stay in that account 10 years or less, choose the TCF account because it's going to have the higher balance each one of those years. If it's going to stay in the account for 20 years or more, then the Wells Fargo account looks like a better option. Because at that point, and then also for any point beyond the 20-year horizon, we know that that Wells Fargo account is going to dominate. So this is a classic example of the kind of thinking I want us to be able to do at the end of this course. And I want to now use this model to continue the process. Now that we know that the answer to the it depends question depends on how long the money is going to remain in that account, let's refine that question and say, in which year? Whoops. Let me get back to the text mode here. I want to make that a note. In which year will the Wells Fargo account overtake the TCF account? In other words, there's a tipping point in here, somewhere between the 10-year mark when the TCF bank account has a higher balance and the 20-year mark where the Wells Fargo account has the higher balance. Somewhere in between these two data points is a tipping point, a place where suddenly the Wells Fargo horse is in front of the TCF horse. I'm sure Wells Fargo would love me making a horse analogy because their whole logo is actually a team of horses pulling a wagon. But that is a corporate plug for you. I haven't received any money for that endorsement. Wells Fargo actually is the servicer for my mortgage for my house, so I have no particular interest in in supporting their lending practices or anything. So anyway, in which year does that worm turn? In which year does Wells Fargo overtake TCF? And when does the purple line, the purple curve, exceed the green curve? That's the kind of question that now has taken our nuance, the it depends question, and put a finer point on it. If we can answer when the Wells Fargo account becomes a better investment than the TCF account, then we can give an even more specific answer to the it depends question. And in order to do that, we do need to cross the bridge of coming up with an algebraic formula for each one of these two types of model. So let's go to that part of the problem next, because this is going to give us the occasion to really think, again, critically about the difference between exponential and linear behavior, and the difference between a slope and a base. So let's start with that TCF account. This is the account that adds $100 every year. If I sketch my data table, I'm just going to copy it down onto my screen here real quick. We're going to use this data table to come up with our equation. So in year 0, the value of this account is $1,000. In year 1, the value is $1,100. In year 2, the value is $1,200. In year 3, it's $1,300, and so on and so on. Going forward this way. Okay. And so the first thing that, again, I want to redraw your attention to is the manner of the change that's happening here in these two quantities. Every time I add 1 year to my x variable, in other words, every time this money is left in this account for 1 additional year, what's happening in the y variable is that we are adding $100. We're adding an amount of money at the end of every year. And that change is consistent from year 1 to year 2 to year 3 to year 20 to year 500, however long we leave this money in the account. For every 1 year that passes, according to the setup of this problem, we add an additional $100 amount to the value of that account. Okay, and so again, the most important thing to observe about that is not just the numbers, but the operation that's being used here. It's addition in my x variable, and it's also addition in my y variable. And that combination is what makes this relationship linear. Addition and addition. Linear. So linear relationships are characterized by having consistent amount rates of change, amounts rate of increase or amount rates of decrease. And we can quantify that amount rate of change as a ratio. That amount rate of change is always the ratio, and when we say ratio, we mean division, right? Ratio of the change in my y value, which in this case is my $100. So I'm going to take that $100 and I'm going to make it the numerator in my fraction here. So plus $100. And then I'm going to take my amount rate, my amount change in x. I'm going to make that my denominator in this change fraction here. So that becomes the downstairs plus 1 year. I divide these two numbers. 100 divided by 1, well, that gives me, that's an easy division problem, right? 100. But when I divide these numbers, I also divide their units. And so I can understand the units of this as dollars on top and years on the bottom. And carrying those units through in this calculation actually helps us to contextualize and explain to somebody who's not taking a math class what this number actually tells us. This number is first and foremost called the slope of my linear relationship. And I can take these units, write them out in an English sentence here, dollars per year. And those units will tell me how to contextualize the meaning of this number. Okay, so this number tells me that for every plus 1 year that passes, the value of the account, the investment, increases by an amount of $100. That's not surprising because that's literally what was told to us about this bank account to help us set up this problem in the first place. But in telling us that information, right, so in giving us this $100 at the end of each year is added to my bank account, they have explicitly told us here that that is the slope of this linear relationship. Right? So that's what this number means. That ends up being the slope of my equation. And for students who like memorizing formulas, which you may be one, remember that slope is this thing that we often give the letter m to represent this relationship. And the formula which we use to compute a slope is literally a difference in y values, y2 minus y1. So here, for example, 1100 minus 1000, right? That's where I would have gotten this 100 number in the first place. And my denominator is the difference in x values that corresponds to it. In this case, that would be, for example, 1 minus 0. So that's where I would get this 1 in my denominator. So it's all part of the same puzzle, right? If you're used to using formulas like m equals y2 minus y1 over x2 minus x1 to compute a slope, this is why that formula does what it purports to do, because it is measuring the consistency in the amounts by which the y variables change and the x variables change between corresponding points in a linear relationship. So the slope of this equation is 100. And now that I know that the slope of this equation is 100, what I can do is I can begin filling in an equation template for this relationship. And my equation template is y equals mx plus b. Y equals the slope times x added to the y-intercept, whatever that happens to be. And now that I know that my slope is 100, I'm just going to drop that number right into my slope parameter. Right? So this 100 is going to give me the slope of my relationship, and so it's the coefficient of x in the linear equation. Now what about the intercept? Remember what the intercept measures, and this is true whatever kind of function we happen to be working with. The y-intercept measures the y value when the x value is equal to 0. So in this example, we actually already have the intercept staring at us in the face. Because when x is equal to 0 in this data, that's my initial investment in this TCF bank account, right? And so it has a y value that's equal to the value of that initial investment. That's this 1,000 number right here. That 1,000 is my y-intercept. So I don't have to do any fancy algebra to figure out the intercept for this example, because I already have it in my data table. Maybe we'll get an example of a situation where we do have to do that arithmetic before we're done with today's review, but maybe we won't. So here then is an equation for my TCF bank account. The value y of the account in year x since the investment was made is y equals 100x plus 1,000. Let's go ahead and add that equation onto our graph here, just to verify that it works the way that we claim that it works. Y equals 100x plus 1,000. And sure enough, that line passes through all of the data points that we speculated would be part of our data set. Okay. So my formula, my algebraic model, is successful for that reason in modeling my data, and it does so perfectly. Right? If I were to run a linear regression on this data, we would get a correlation coefficient exactly equal to 1, because this line passes exactly through all of my data points. Because in reality, this data didn't come from measurements taken that are subject to noise and measurement error. This data was generated by an algebraic principle, the principle that every 1 year that passes, we get an extra $100 in this account. So of course it's a perfect correlation with the equation that models that very same consistent change behavior. So that's for the TCF bank account. It's a linear function. Its slope is 100 because it earns $100 of additional money for every 1 year that passes. And its intercept is 1,000 because that was the value of this investment when the year after investment was 0. In other words, when the account was opened. So now let's turn our attention to the Wells Fargo model. This is the one in which we're earning 6%, exactly 6%, for every year that passes. So how does that change the game? So for the Wells Fargo account, let's put in our data table once again. And again, I'm just going to put in the first few data points. All we really need to convince ourselves of the fidelity of this data is we really only need 3 data points. 3 data points are enough to determine whether something does lie along the same straight line or along the same exponential curve that has 2 parameters for the exponential function. So I'm just going to put in, well, maybe I'll go up to year 2, sure. And so this is 112360. And again, what made this an exponential relationship is that for every 1 year that passes, so anytime I add 1 to my x variable, the same consistent change is happening to my y variable, but the nature of that change is no longer addition and subtraction like it was with the TCF account. Now it's multiplication by 1.06. Multiplication by 1.06. By the way, if I wanted to go backwards, this is something that I notice occasionally gives people some fits on quizzes. If I want to go backwards in an exponential equation, this is where it really helps to think about this change as being multiplication. Because then that tells me that in order to go backwards, what I really want to do is instead of multiplying by 1.06, if I'm going backwards, I want to divide by 1.06. So that's a parenthetical that I wanted to make sure to throw in there because I noticed that was tripping some people up on one of the recent quizzes that you took. So here's my consistent nature of my change relationship in this example. And now, because it's multiplication in the y quantity related to addition in the x quantity, that fundamentally changes the nature of this relationship. And it's that comparison, it's that pair of multiplication in the y and addition in the x, that is what makes this an exponential function instead of linear. Right? If this were addition and addition, we would have a linear relationship. But it's addition in the input, multiplication in the output. That gives me an exponential relationship. So every time I increase my number of years by 1, I multiply my bank account value by 1.06. Okay, so let's then put in a template for an equation model that could help us to understand what's going on here. Right? My exponential functions are all going to have an equation template, a model that looks something like the following. I'm going to have a quantity here out in front, which we call, again, our intercept. And then I'm going to have an exponential expression that comes next that has a base and that has then an exponent. And the x lives up in that exponent. So the difference between a slope and a base, well, what's the same about slope and base? Slope and base are the same in the sense that each of them characterizes the consistency of the changes inherent in the relationship between two quantities. The slope of a linear relationship tells us what the constant amount rate of change in that relationship is. The base of an exponential expression tells us what is the constant percentage rate of change that exists in the relationship between those two quantities. And so, in our example here, if I wanted to know what the base of my exponential expression is here, it's an answer to the question, when x is increased by 1, so when I add 1 to my independent variable, my input variable, my x, the question is, what is y multiplied by? So we know that in an exponential relationship, addition in the x quantity is intertwined with multiplication in the y quantity. And so the base of an exponential expression answers the question, when x has 1 added to it, what is y getting multiplied by at the end of each one of these years in this example? Well, the answer here is already staring us in the face, because we have in our data, in the x variable, my number of years is changing by +1 each time. That's how we got this data in the first place. And every time that the x variable changes by +1, the value of the y is changing by multiplication by 1.06. So this 1.06 is exactly the base of this exponential expression. That is the answer to the question, what is y multiplied by every time x is increased by 1? So if we happen to have a data table that's this nice, right, where we have increases by 1 in the x variable, then the amount that y is being multiplied by for each one of those increases of 1 in the x variable is what we mean by the base of my exponential equation. So I'll fill in the base here, 1.06. Okay. And so that's not really worth overthinking from a computational perspective. This model looks a little bit different than the one that uses the natural number e in it, which we will talk about in a few minutes. But just for the sake of getting an equation onto the page that will help us to understand what's going on here, having 1.06 as the base is exactly what we want. And then we use that 1.06. We can recontextualize what that number means, right? Because to multiply something by 1.06 is the same as to multiply it by 106%. Right? But that's the same thing as multiplying it by 100% and then multiplying it by 6% and then adding those results. But multiplying something by 100%, multiplying a quantity by 100% doesn't actually do anything. And so what this number is really telling me is that for every year that passes, for every +1 year that passes, the account, the value of my account, increases by 6%. After all, that's exactly what was told to us in the setup of this problem. That's where we got this data from, and now it's being borne out in the base of my exponential expression being 1.06. Okay, so now I know what the base is. What about the intercept? Well, just like in the linear example, the intercept is characterized by being the y value corresponding to the x value of 0. So once again, just like with the linear model, my intercept is found in my data table right here as my y value corresponding to the x value of 0. So once again, just like for the linear model, the intercept in this particular equation is 1,000. And so from this equation template, we then have a model for an exponential equation modeling this data. Y equals 1,000 times 1.06 to the power x. And something is a little bit out of joint here. What did I screw up? Oh, that's what I screwed up. Sorry. Now, of course, that I fit this equation, so let me turn this into a teachable moment here, because I screwed something up, and that happens. So notice that when I put this equation in, it doesn't actually match up with the data points that I have over here. And that must mean that either my data points were computed incorrectly, or that my equation that I wrote down here was not correct. And actually, the error, as I'm looking at this, is not in my equation. The equation exactly conveys the information that we had about this Wells Fargo account, that we started with $1,000 saved in year number 0, and every year the account is earning 6% simple annual interest. And so the equation is not at fault here. It's actually my data. And the reason that my data went awry, let me zoom into my browser for a second, is in my little calculator here, I wasn't using 1,000 as my base, or as my intercept. I accidentally had 1,060. So that's what happened. Let me go back in and fix that data point. So at year 20, we should have 3207.13. So I'll fix that one here, 3207.13. And at year 10, 1790.85. There we go. And now, once again, my exponential equation is passing through all the data points that it needs to pass through. Okay. So we have now our two different equation models. You can see them here on the left side of the screen. Y equals 100x plus 1,000. That's the linear model that models my TCF bank account, which is increasing by an amount of $100 every year. The purple equation, y equals 1,000 times 1.06 to the x, is my Wells Fargo account, which is increasing at a 6% increase at the end of every year. So let's return to that question that I posed, which is, which account is better? And the answer that we gave initially is still true, right? That for the first few years of the investment, the TCF account, the green line, is doing better than the Wells Fargo account. The linear model is giving me a better rate of increase than the exponential model is. But at some point, things change, and the Wells Fargo account ends up overtaking the TCF bank account. So that by the time we get to year number 20, the Wells Fargo account, which was earning a percentage increase of interest every year, that account has a higher balance than the TCF account does. So let's come back to this question. In which year does the Wells Fargo account overtake the TCF account? That year we can find in the graph as being the point at which these two graphs intersect. So a decent graphing calculator, or Desmos, which is one of the most decent graphing calculators available, can estimate a value for this. So 17.126. But of course, we'd like to be able to do this with algebra. That's our ultimate goal. Unfortunately for us, we actually don't have the algebraic tools in our course to find where these two models intersect one another. We're going to have to rely on something numerical in order to do this with some degree of certainty, or something graphical like Desmos. Because what we would have to do in this example to algebraically find the intersection point is figure out where this expression for y, the value of my account, and this expression for y, the value of the other account, are equal. So I'd have to set these two expressions equal to one another and then solve for x. The problem is, one of these expressions has an x that's outside of an exponent, and the other one has an x which is inside the exponent. So the problem is, if I try to rescue one of the x's from the exponent, the other x is going to get trapped inside a logarithm, and vice versa. If I don't get the x out of the exponent, then one of them is in the exponent, the other is not. And so I can't ever get those x's just by using algebraic tools to be on the same level as one another to where we can set these equal and get the x by itself. So we're not going to be able to do this piece using just the algebra that we know in this class. And not only that, I'm a mathematician and have been for 15 years at this point. And I have not learned any algebra that is capable of doing that symbolically. We have to rely on something that is numerical in order to do that. So based on the evidence in this graph, let's change the question a little bit. So according to this graph, at the point at which the Wells Fargo account overtakes the TCF account, the value of those accounts, the amount of money in those accounts, is the Y value. Here it's 2712.573. So let me change the question here. In which year will the Wells Fargo account grow to have let's say $2,175 in it? Question mark. So that $2,175, let me just put that on my graph here real quick. Y equals 2175. Whoops, I think I must have gotten that number wrong. 2712. I just had a little touch of transposing these digits here. Let me change it to 2750 then. Y equals 2750. So what that does is it kind of sets this horizontal line at 2750. And so I want to know, when does the purple graph exceed that line? When does that happen? So here now is an occasion for us to use some algebra to get this solved the way that I want to get it solved. So let's turn to that as the last task that we have for today's live stream. And I'm going to have to change the game a little bit one more time in order for us to do this in the way that I've been sort of leading us through how to do this in the past. So if I want to know, when does the Wells Fargo account, that's the one that we've modeled with an exponential function, remember? So when does the Wells account have $2,750 in it as a balance? Then the first thing to know is that 2,750, because it's a balance on this account, that 2,750 is going to be a value for y, not a value for x, right? Because my y-axis here is what's recording the value of my investments. The x-axis is telling me the number of years since investment. So this is a type of problem where I know a value for y, and what I'm trying to do is I want to try and find a value for x, because the question is asking me when, right? And the answer to a when question is going to be a number of years. So I know y, and I want to find x. And the equation that I have that relates y and x is this: y equals 1,000 times 1.06 to the power x. Right. Okay. Well, there's a bit of a problem with this equation compared to the exponential equations that we've learned how to solve using the tools of our course up until this point. And the thing that is causing me a little bit of heartburn with this equation is that we don't see the natural number e in this equation anywhere. So I'm going to do this for you as the instructor for this course. So this is not a process that I'm necessarily going to expect you to replicate, but you may be interested in how this part actually works. What I want to do is I want to change this equation into one that has a base of e instead of a base of 1.06. So how am I going to do that? So the secret to how to do that, it's not a secret really, I don't want to oversell it, but the secret is that in order to make this happen, I need to understand what power of e is equal to 1.06. If I can figure out what power of e, the number e, is equal to 1.06, then I just have to replace 1.06 by e raised to that power, and I will get a function model that looks like the p times e to the rt kind of model that we're used to when thinking about equations for present value, future value, compound interest, all those wonderful kinds of things. So the question I'm asking myself here is, what number, what exponent should I put here on my e to make e raised to that exponent equal to 1.06? Often this exponent is called r. And the reason it's called r is that this r becomes what we call the continuous rate of increase. continuous rate of growth for this particular exponential equation. And so what I'm trying to do here, again, this is over here on a sidebar, so don't fret too much about replicating this process in your own work. I want to know what value of r makes e raised to the power r equal to 1.06. So this part you should know, because this is vital to what we're about to do. I want to get this r, this exponent, by itself. I want to solve for it. But it's trapped inside of this exponential, right? It's in an exponential where it is the exponent and the base is the number e. And so what I want to do is I want to somehow get rid of that exponential, get rid of that base of e, so as to get the r rescued by itself. I want to undo the exponential function. How do I do that? I do it with what's called the inverse function to the exponential function. That inverse function has a name. It's called the natural logarithm. Natural because the base that we're canceling out here is e, which is called the natural number. It's roughly equal to 2.71828 and so forth. And logarithm because it's the opposite of an exponential. So it's what rescues something from an exponent. And natural logarithm is better known on a calculator as ln. That's the abbreviation, is the ln button. And so what I want to do here is I want to take the natural logarithm of both sides of this equation. On the left-hand side, it has the effect of rescuing my exponent from the base of e that it's wrapped up in. And on the right-hand side, it has the effect of replacing 1.06 with the natural log of 1.06. I'm going to use Desmos as my calculator here for a second. And just ask Desmos, what is ln of 1.06? And it gives me this decimal, 0.058268 etc., etc. I'm going to round that off and keep a few decimals, but I don't want to keep all of them. I couldn't keep all of them because there's infinitely many. 0.058269, let's say. Okay, so I'll round it off right about there. Okay. So the value of r that is going to make e to the r equal to 1.06 is about this, 0.058269. So I'm going to replace the r that I had over here with this number, and then we'll be one step away from having a kind of equation that we know how to use the tools of natural logarithms in order to solve. And again, this is a process that I will have done for you in the setup of similar problems like this on an exam. So don't worry too much about how I just did this. Worry most about what's about to happen next. 58269. And then that is being raised to the power x. And then my last step is to use the so-called properties of exponents. And the properties of exponents say that when I raise a base to an exponential power, and then I raise that power to another power, so when a power meets a power, when a power is taken of a power, those exponents can be multiplied and applied to the same common base. In other words, e to the r quantity raised to the x is the same thing as multiplying the r and the x and using that as my single exponent on my e. All of which is to say that that property tells me that the parentheses that I put in here to wall off my exponent from the x that follows it are not in fact necessary. I'm going to just strike those parentheses using properties of exponents. And now what I have is an equation that should look more familiar to the kinds of equations that you're used to solving from our homework over the past couple of weeks. Right? Y equals 1,000 e to the 0.058269 times x. Right? So this is the form of the exponential equation model that we are equipped to use natural logarithms in order to solve and therefore come out with the answer to the question that I've posed here. So let's do that bit. Ooh, my coffee's getting cold. It's been a long hour. It means that we should be wrapping up here pretty soon. When the coffee's cold, you know that's when the math is almost done. So let's return to what we were trying to do. We wanted to know what is the value of x when the value of y is 2,750. So what that suggests is I take the number 2,750. I substitute it for my y in my equation, and then I have 1,000 multiplied by the exponential with a base of e, and the exponent is 0.058269 times x. Okay. And so now again is where I look at the expression that I have on the right hand side and ask, what is it going to take to rescue that x, to get that x by itself? That's what we're trying to do whenever we're solving an equation, right? If we're trying to get that variable by itself. So at the end of this process, we want x equals blank. And the meaning of this blank, of course, because x is my time since investment, this is going to be a number of years, right? So that's one of Stephen Covey's 7 habits of highly successful people. Begin with the end in mind. I think that's maybe even habit number 1 in that book. So we're beginning this process with the end in mind. We want to get x equals blank. Right? We want to rescue the x. The problem, of course, is that x is wrapped in 3 layers of arithmetic. I like this metaphor a lot, so I'm just going to keep hammering it home. I've got x. And if I'm x, the order of operations in this expression on the right-hand side of my equation is saying the first thing that's happening to me is I'm getting multiplied by this number, 0.058269. And so it's a bit like x is wrapped up in a layer of wrapping paper, and that layer of wrapping paper is the arithmetic operation multiplication by 0.058, 0.058269, multiplication by 0.058269. That's the first thing that's happening to x in the order of operations here, because this exponent is implicitly in a little teeny tiny set of parentheses, right? So PEMDAS says, do that thing first. But then after I'm multiplied by 0.58269, the next thing that happens to me is this exponentiation, right? Because exponents come before multiplication in the order of operations. That exponent happens before the multiplication by 1,000 does. And so the next layer of wrapping paper is my exponential function. I'm going to just write exp, right? And then finally, the last layer of wrapping paper is multiplication by 1,000. So that's the very last thing that happens. My outermost layer of wrapping paper, multiplication by 1,000. And again, I use this little graphic here to suggest the order in which we should be undoing, the order in which we should be unwrapping these layers of wrapping paper is the opposite of the order in which they were wrapped in the first place. If I were wrapping this present, I first would have wrapped the inner layer, and then the middle layer, and then the outer layer. But if I'm unwrapping this present, I have to unwrap the outer layer first, then the middle, then the innermost. So where PEMDAS tells me how to evaluate an expression, it's the opposite. It's SADMEP that tells me how to undo, how to unwrap a variable from inside of a combination of arithmetic. So all of this means that the first step that I'm going to apply in solving this equation is to undo the last step that was done when this thing was sewn together. So the first thing I want to do is undo this multiplication by 1,000. That means the first thing I want to do in this equation is divide both sides by 1,000. Divide by 1,000 on the right side, divide by 1,000 on the left side. When I divide by 1,000 on the right side, it's going to have the effect of turning this 1,000 into a 1, and multiplication by 1 is invisible. So we can think of it as just canceling that 1,000 from the right-hand side and leaving me with just e to the power 0.058269 times x. So the right-hand side of my equation has gotten one step simpler. We've torn off one layer of wrapping paper. And now the left-hand side of my equation, I can find 2750 divided by 1,000. That's 2.75, using a calculator or what have you. Right? So now we have completely unwrapped the outer layer of wrapping paper. So this part is no longer here. And so now the next layer of wrapping paper that we have to deal with is that middle layer. It's the exponential function. And so here is where we use the same trick that we used up here, right? How do you undo an exponential function whose base is e? That is exactly what the natural logarithm exists in life to do. And so my step now is to take a natural logarithm of both sides of this equation. So to unwrap this box, we're going to use the natural log. So that means I'm going to take the ln of the left-hand side of this equation, and I'm going to take the ln of the right-hand side of this equation. And again, the entire purpose of ln is that it undoes the exponentiation with a base of e that we see on the right-hand side. Okay? And so when it does its work, I will have rescued the 0.058269 times x from out of the exponent in which it was previously trapped. And then the left-hand side of my equation, I'm going to have the natural log of 2.75, which again, pull out a calculator, it's going to be a nasty number. Natural log of 2.75 is 1.0116, roughly. Again, rounding just a little bit. There we go. Okay. And now that I have unwrapped my exponential, now there's only one layer of wrapping paper left before I can get to that x. And it's this multiplication by 0.058269. And we know how to undo multiplication in an equation. That we learned in our basic algebra class that came before this one. I just have to divide by 0.58269. On the right side, which gets rid of that coefficient, and on the left side, 0.058269. And that division undoes my last layer of wrapping paper. And it's going to leave me with just the x, which is, after all, what we wanted when we were beginning with the end in mind. Right? So all that lies between me and the final answer here is to do the division problem on the left-hand side. 1.0116 divided by 0.05269. Divided by 0.058269. And that gives me roughly 17.36, according to my calculator. And so that then, 17.36 years. That then should tell me how long it's going to take for the TCF Bank investment to grow to $2,750. And sure enough, right here is that point on the graph, right? The point on the graph when the x value is 17.361, so we're at 17.36 years, a little more than 17 years and 4 months into this investment. And the y value, the value of the account at that point, is $2,750. So most important thing on this last slide here to take away, I guess two things. First of all is slow your thinking down when it comes to thinking about how to unwrap an x from an expression into which it's been integrated here. Because thinking carefully about how the order of operations knit this expression together will help you to think carefully about how to unwrap those layers of arithmetic that are surrounding the x so as to get x by itself. And remember that the order of operations in that process works backwards because it's unwrapping something that the regular order of operations had wrapped up in the first place. That's thing one. And thing two is the role of the natural logarithm. What does it do? The whole purpose of a natural logarithm is to get rid of an exponential expression where the base is equal to e and rescue the exponent from out of that expression. So anytime we have e to the something and I want to end up with that something instead, if I want to get rid of the e and take the stuff from the exponent down so that I can solve for x, for example, the natural logarithm is exactly by definition the tool that exists to do that. And that is as much as I care that we know in this class about logarithms. If you get that step that happened right here, right, and also happened up here, if you get that step, you get as much as I care for you to get about logarithms for the purpose of our course. So I hope that today's example, again, just one example with, again, thanks to my old school district, 622 in North St. Paul, Maplewood, and Oakdale, Minnesota, for sharing this this problem resource online. If you like Math 105 students, I can share with you this whole packet because it actually leads you through a bunch of other explorations of data and comparing linear to exponential functions. I think this is really good practice as well. So I will share a link to this in the YouTube notes for this video. I'll also share it with you via Slack. It's got the answers at the end as well, so you can use it to check your work. But really, the process of sorting out what is the difference between linear and exponential behavior is exactly the process of sorting out everything that we needed to know in this unit for exam number 2. So good luck on the rest of your exam. If you're working on the exam, you're one of my students, feel free to hit me up with any questions in the Slack channel, or if it's a question that the whole class would benefit from, put it in the math channel or the doctor's office channel inside of our Slack account. And then after we get through exam 2 this weekend, we're going to turn a quarter and we're going to radically change the activities that we do for the rest of the semester. I'm going to introduce our semester project and also talk a little bit about how we're going to consolidate some of the work and make it a little bit easier to earn mastery on these last topics of the semester, where you're going to deal with statistics and statistical literacy. I'm really looking forward to this last act in our course, and I'll see you then.